So this is actually a famous example where polar coordinates come to play, and you may be thinking, wait, polar coordinates, this is only a single integral function of one variable. What are you talking about? But let me show you. So this is a famous function. If I graph the integrand, e to the negative x squared, it's this Gaussian shape, and this is going to show up a ton in statistics, signal processing, image processing, and more. And so we're often interested in trying to evaluate this integral. It does not go below the x-axis. Let's make that very clear. We're interested in evaluating this integral. In particular, we want to know what would happen if we evaluated it over the region negative infinity to positive infinity. Okay, so we know we're stuck because there's no closed form antiderivative for this, which we talked about earlier. So I can't just do this using like, oh, integration by parts or something like that. But here's a trick for this, just for this particular example, okay? The trick is I'm going to let I'm just going to call this integral I. Okay, and this trick is not something, and you could do it in other problems, but it's really just kind of famous for this specific example. I just wanted you to see it since this is a famous example. All right, I'm going to call this integral I, and now I could say, well, then I squared would be this integral multiplied twice. And I'm going to do it again, but I want you to notice with integrals, I'm just using dummy variables. I can actually use a different dummy variable if I'd like to here, because at the end of the day, this is either going to diverge or it'll converge to some number. Okay. We're going to figure out what it is in a minute. But this to me looks like, if you think of it, as a double integral that's been decoupled. So let's recouple this double integral. And I can write it like e to the negative x squared times e to the negative y squared dx dy, which just ends up being e to the negative x squared minus y squared. Wait, this is looking very familiar. Yes, this looks almost identical to our warm-up. The only difference is our region. So let's do this problem. Let's switch to polar, and let's see how this changes our region. Okay, so I'm now, let's do the integrand first. We did that before in the previous example, e to the negative r squared, and then my dx dy becomes r, dr d theta. And let's think of what the region itself is going to look like. I'm going from negative infinity to positive infinity in both x and y. So it's all of the xy plane. Oops. Let's just color the whole thing. It's this whole thing keeps going forever. Okay. Let's start with r. So we are going to shoot radially outward from the origin and tell me where r enters and exits the region. So if you're noticing, r, when we're setting this up in, we're setting integrals up in polar, we're never going to allow r to be negative because we'd like a unique representation for each point in the xy plane. So to do that, we limit r to always be positive, and then we allow theta to just span one full circle. Okay, so r is starting at 0, but r goes all the way out, keeps going. So r continues on to infinity. Theta, we're just going to allow this to, again, sprinkler around. The smallest theta that I can have, I'm only going to do one rotation so that I don't double count points. The smallest theta I can have is 0, and the largest is 2 pi. Or you could do any other, you could start at negative pi over 2 and come back around to 3 pi over 2. That part's fine. You just want to make sure you only count points once in this region. Okay, so now we can do this by decoupling again. This is now 0 to 2 pi d theta. And now I have this integral. And if you're thinking, wait a minute, I don't have constant bounds, why did she decouple? Because remember, when you're doing improper integrals, the whole method is we replace, so let's let's just do that part, right? Let's do this 2 pi real quick and then get to the improper integral. We replace what we have in the integrand with a constant. So that's how I knew I was going to be able to decouple. Replace it with a constant, and then we take the limit as that constant goes to infinity so that we can use the fundamental theorem of calculus to evaluate. Negative r squared dr. Okay, great. And then let's write out what we get. So this is 2 pi, and then I'm going to have the limit as k goes to infinity. Okay, again, just doing the antiderivative in our heads and plugging in. I'm getting negative 1/2 e to the negative k squared plus 1/2. Okay, but notice when I take the limit, this term is going to go to 0 because I'm going to have an e to the k squared in the denominator. That piece will go away in the limit. This is going to 0, which is going to leave me the final answer of just 2 pi times 1/2, which is just going to give me pi. Okay, now I'm not totally done yet because if you recall, what we just found was I squared. And originally, I was just interested in I. So we can go back up here and we can say, therefore, since I squared is pi, that means this original integral we were interested in finding does in fact converge to square root of pi. So that's this area underneath this Gaussian curve from negative infinity to infinity. And we find it converges, keeps going here, but it converges to square root of pi. So that's a cool famous example, and I love it because you can't actually do it just using functions of one variable and what you knew from Calc 1 and 2 analytically, but you can do it now that we have polar coordinates and double integrals. Okay, now I would say generally there's not another example where you would need that specific trick. It just that integral comes up a lot in later applications, so I always like to make sure you've seen it. Now let's just go to a general double integral and give you some more practice setting it up. And we're going to combine some things that you learned in the recitation video about center of mass now, and have you figure out the center of mass of a plate if the density at any point is proportional to its distance. So go ahead and put this on pause. See if you can put together everything we've learned and figure out this center of mass. Okay, so our region, let's sketch that first. This is these 2 semicircles. Okay, so here's one, and here's the next one, and it's the part that joins them. So this is 1 and 2, and let's shade this in. So it's this is R. That's my little plate. Okay, and I like to find the center of mass of the plate if the density at any point is proportional to its distance. So first, let's come up with an equation for the density. The density is proportional to the distance. So proportional means we just have a scalar multiple times the distance to the origin. So I can put that as k, and then my distance to the origin is just going to be square root of x squared plus y squared. And then I can ask how I find center of mass. So center of mass of the plate is going to be my average weighted x location and my average weighted y location. And if you recall from the lecture on this is given by this divided by my total mass, that's in my denominator here. And then y is given by, it's my like your average y location weighted by your density. And then I'm dividing by the mass. Okay, so I have all these integrals I need to do, but because my region is part of a
Mama, can
circle.
You do the rest later?
Yes, give me 1 second, okay? Because my region is part of a circle, I'm gonna need to switch to polar. So take these, put it on pause, switch to polar, and I'll continue in a minute.